Todd is the director of software architecture and is also a senior principal engineer leading software architecture for high-performance networking Ethernet products at Intel. Previously, Todd was the lead software architect for Intel OmniPath Fabric. Todd has over 20 years of experience with HPC. He's been active participant in OFA as well. He contributed to RDMA, OmniPath, and InfiniBand. And overall, he spent his career working on high-performance I/O and servers. Prior to his current role at Intel, he was an architect for InfiniBand products at QLogic and the chief architect at Silverstrom Technologies. 37 patents, Todd. That's impressive. Thank you. So there we are. Jude, are you able to find the slides, the right ones? Okay, there we go. It's coming up.
There we go.
Thank you. Todd, stage is yours.
Okay, thank you. Thank you very much. Thank you for the introduction. Welcome you all here to the Open Fabrics Alliance. It's certainly some interesting times. I wish we had the opportunity to all be together in person, but this is certainly an effective and fun way to present. Next slide, please. So I'm going to talk to you today about some work we're doing that we refer to as PSM3. And these are some of the topics I'll be touching on. So we're going to talk a little bit about what it is. It's a new lib fabric provider, and I'll walk you through some of the architecture for that and some of the key features. The focus of this effort was designing it for Ethernet and Rocky, trying to optimize the performance and scalability of RDMA and Rocky for the Ethernet environments using HPC and AI. And we've built it in a way that will work on top of standard Rocky protocols and interfaces. Also at the end, I'll show you some links. The code is available upstream now. We've already been able to integrate it into libfabric, and there's some out-of-tree available versions of it that'll work on some of the older existing distros. Next slide, please. So the PSM3 architecture fits naturally into the Open Fabrics Alliance's architecture for HPC and AI environments and RDMA in general. So this is a libfabric provider that fits within the libfabric infrastructure. Libfabric, as you're aware, is the Open Fabrics Alliance's focus for many middlwares that need high performance messaging, such as various MPIs and other applications such as AI training. This fits naturally and adjacent to existing interfaces that are used for other forms of I/O, such as sockets and verbs, all of which have various elements in the Open Fabrics Alliance capabilities. Our focus here has been to make sure that this provider runs very well on Ethernet drivers, such as the Intel E8000 or E800 drivers that have come out this year for the NICs that we're currently shipping. But it'll also work on some other environments. It also enables communications for more extensive environments that are being developed in the community, such as the One API initiative that's providing a general framework for computational environments involving CPUs, GPUs, and/or accelerators. And this fits naturally into the communications portion of those environments. The code is built on top of the standard Rocky capabilities, and I'll walk you through some of the features here. It's designed in a way that it fits in transparently, so existing HPC applications do not need any code changes, and actually will run under existing middlewares that take advantage of libfabric. Next slide, please. So one of the biggest challenges in the modern world with high core count CPUs is scaling so you don't need excessive number of queue pairs or excessive number of communications resources or excessive amounts of memory for communications. And so, if you took a direct approach of simply establishing RCQ pairs in process-to-process connections, you would need a very large amount of Q pairs in memory. Even at 100 nodes, you'd be starting to talk about hundreds of thousands of Q pairs, many gigabytes of memory. And this is exacerbated by the very high core count CPUs that are available. One example would be, a CLX AP socket can have up to 56 cores with 112 for a hypertransport in at least one of its SKUs. And there's a variety of other processors and SKUs in the industry that have equally high core counts, and certainly you can build multi-socket servers that further increase that number. But this kind of becomes a quadratic problem. The graph shown here is a log-log scale, and so you can see it's a quadratic problem to be solved. And it's driven by a number of factors: the number of Q pairs that you need, the number of Wookiees you need to put on those Q pairs, and then the receive buffer space that backs that up. And of course, in at least the MPI world for HPC, you often have one rank per core, so you do need all these resources. And so, the PSM3 solution addresses this problem with approaching it with a UDQ pair for eager and control protocols, and I'll talk through what I mean by eager in a couple of slides. And so this allows us to have one UDQ pair per process and the corresponding receive buffering for it. So then the scalability from a memory and a Q pair point becomes linear relative to the number of processes per node, and we can reduce the amount of connection state by using very efficient connection establishment and connection handling mechanisms in the software that need less resources than some of those that are implied by RCQ pairs. So connection state is still a little bit of a quadratic component, but it's a much smaller coefficient. And so we end up in the end saving about an order of magnitude or 2 orders of magnitude of memory and Q pair resources. Now, RDMA is still very important, and it's very important for direct data placement. So to get back those capabilities, we take advantage of a kernel level node to node Q pairs, RCQ pairs, that will be used for Rendezvous with direct data placement and RDMA for larger messages. And this gets us the best of both worlds with a minimized footprint in terms of number of Q pairs and amount of memory, while also retaining all the excellent attributes of using direct data placement and RDMA for data transfer strategies. Next slide, please. So this is the basic high-level architecture. I have some more detailed slides that'll be coming up. So by taking advantage of UDQ pairs per process, we get very good latency and very good scalability, but we can then still use the RDMA for Rendezvous. And we implement a kernel Rendezvous module as a helper to PSM that provides these shared RCQ pairs and some other features that I'll discuss here. And so this changes the scaling equation for number of Q pairs to be a linear equation of nodes plus process per nodes, as opposed to a quadratic equation. Keeping the number of Q pairs small and the amount of Q pair state needed in the adapter small also helps to keep the Q pair caches very hot. So in a typical environment here, you may be using tens or hundreds of Q pairs, as opposed to the alternatives that might use thousands or millions of Q pairs. And so this lets those caches stay hot. It keeps avoids latency jitter and helps to avoid other overheads such as extra PCI transactions to refresh Q pairs when they're not available in the on-chip cache inside of a NIC. The shared Q pairs are shared across all the processes in a single job for a single user code. And so this allows the job to have different jobs can have different sets of Q pairs, avoiding interference between jobs. And we can actually also have multiple Q pairs, so we can stripe data across those processes across multiple Q pairs while containing the number of such Q pairs to a small number, so that we get the benefits of that parallel delivery while not needing very many resources. In order to support RDMA, we also do MR caching in this Rendezvous module. This again is a per process cache of its memory regions and allows us to be more efficient on when we have to register new buffers for use in RDMAs. And in most cases, those buffers are going to be frequently reused, and this gives us a notable benefit in performance and overhead for setting up those RDMAs. By taking this architecture, we've also been able to implement an automatic Q-pair recovery mechanism so that we can recover both in PSM and in the Rendezvous module from lost Q-pair connections, whether it's lost packets for UD transfers that are occurring in user space, or lost connections for RC Q-pairs, perhaps due to exceeding the retry count on a Q-pair. Many of these concepts are not new. These are concepts that are a casting of things that we explored in OmniPath and previous generations. And so we've looked at the mechanisms and the advantages that were available in those solutions and recast them onto a standard Rocky capability. Next slide. So there's two basic data movement strategies. Those of you that are familiar with how two-sided communications are often implemented inside of MPI or other two-sided messagings are probably very familiar with this. So the first strategy is an eager strategy. You want the lowest latency, especially for smaller messages where control overhead and latency are the key elements of the latency. So you take advantage of what is referred to as an eager strategy, in which case you actually do have bounce buffers. You get the things in flight as soon as possible. You let the sender move forward as soon as possible. For example, in the MPI standard, a sender just needs to know that its send buffer is free for reuse. It doesn't have to know that the recipient has actually received the data and delivered it. So it's a matter of ensuring that you can deliver it and getting that buffer freed on the send side so that the application can do other things as quickly as possible. And then on the receiving side, you can land the data even if you don't have a posted MPI receive yet, do the tag matching, and then move the data out of the bounce buffer. And then for smaller messages, these bounce buffers are very tiny overhead in the overall latency. Now, for larger messages, you want to get rid of those CPU copies. You want to take advantage of RDMA and direct data placement, but you do have some extra overhead, so it's a balancing act because now you have to exchange R keys for the exact destination buffer, and the sender and the receiver have to know where things are going to go. And so the strategy here is kind of a traditional rendezvous protocol where we do a request to send that includes things like the tag and other identifying information for the sender. This allows you to then do tag matching on the receiver. Once you have the posted receive and have successfully matched the tag, we can register the destination buffer and send it across with a clear to send indicating the R key and what portion of the transfer we want to have done. In response to that, the sender issues an RDMA write, which may be multiple packets, and we actually take advantage of an RDMA write with immediate so that the recipient can take the immediate as an indicator of completion of that transfer, and the immediate data indicates the exact transfer that was identified in the CTS, so the receiver knows when and which transfer has been completed, because the receiver may have many such transfers in flight at a time. The RDMA write, of course, gives a completion to the sender, which notifies the sender that the buffer is now completely done being used, and permits the sender to free the buffer and start using it for other purposes. Now, this is a simplified version of the picture. There are other advanced features that are available and happen here. The data can be striped across multiple NICs. This would involve different clear to sends for different portions of the transfer, in which case we can get multiple transfers going on in parallel across different NICs for a single large message. The clear to send can also be pipelined so that we may have multiple clear to sends even using the same NIC. And that allows us to pipeline some of the memory registration and memory pinning when that's occurring, so that we can get things started rolling on the first chunk of the message while we may be pinning additional memory for additional receive buffers on the remainder of the message. We also do things like hiding the registration on the send side, because once we send the RTS, we can anticipate that we'll get a CTS in the future, and we proactively start to register that memory so that by the time the CTS arrives, it's all registered and ready to go. And so that also helps to hide some of the latencies from basic activities like memory registration. And of course, there's caching going on for the memory registrations, as I alluded to, so that for most applications that use the same set of buffers frequently, those registrations on the second call will be virtually free. This is common in operations like collectives, and many applications have a relatively small set of buffers that they're going to use, and the caches can technically be rather large because most computational applications try to avoid swapping to begin with, so they're going to limit, so the ability to pin large amounts of memory is viable. So the caches can grow and relatively large if you like them to, and that's all also configurable. Next slide. So there's a lot of advanced capabilities. These are capabilities we're able to bring forward by starting from a mature software base. There's a lot of other optimizations for various CPU models and CPU modes and operations. But these are a few of the high-level ones that are worth touching on for the amount of time we have available today. So there's multi-rail capabilities. This is especially interesting to artificial intelligence training, where you can have a large bandwidth requirements, and you may want to put multiple NICs in a node in order to get more bandwidth into the node. And there's at least 3 strategies and subtle ways that these can be configured however you desire. So one simple method that works very well, especially in HPC, is to assign a single NIC per process. You already have many processes per node, and so by giving them each, by putting a small subset of those processes on each NIC, you get a good distribution of traffic across all of them by the inherent comms patterns in the app itself. The next mechanism is to start assigning multiple NICs per process, in which case the messages will be round robin striped across the NICs, and larger messages will actually be chunked up and striped across multiple NICs to accelerate the latency and the bandwidth you get for an individual large message. Now these can be configured in multiple ways. You can configure what would be referred to as a single plane or a single fabric. In this scenario, you connect all of the NICs on all of the devices to the same network. Any NIC can talk to any other device. And this can be a very simple config, especially if you've got a small number of hosts, you want to connect them all to one switch. This can be very cost effective. As you start to scale up, the cost of building a fabric with 2 or 4 times as many NICs in a single fabric may increase. You may need to add tiers to a class topology, or there may be extra costs in other topologies. So a multi-plane becomes very interesting, where you can have multiple fabrics that are virtually identical in their layout, and each server has a NIC connected to every plane. And then the strategy here clearly has to check and make sure the NICs on a given process are accessible on all the planes, and the data can still be striped across the planes. It can be round robined across the planes. And so this provides a way to manage the costs of having the larger configuration while getting all the benefits of the striping and round robin mechanisms. There's also a multi-endpoint capability where you can have multiple endpoints opened by a single process on a single NIC. This can help with multi-threading and some other load balancing strategies that we've found useful in applications in OmniPath, and so we've carried that capability forward to PSM3. All of the strategies are tunable. I've talked a little bit about Rendezvous and Eager, and I've mentioned some of the load balancing mechanisms. These are all very tunable. There's a modest set of tunables that let you adjust the behaviors, the crossover points for when to do eager or rendezvous. And for various applications, they may provide some fine tuning of the performance. The defaults are designed to work very well for the vast majority of apps that we've tried, but there are opportunities to experiment and try to tweak the last few percent out of some applications. The design is very resilient to fabric disruptions. A common scenario is that you have a long-running job and you may have some unanticipated disruption in the fabric. Maybe a core switch fails, maybe links fail, maybe even the link going to your server briefly has an outage. Maybe there's a sysadmin mistake that bumps or moves a cable or hits the power on a device that you didn't expect. And so it can survive these kinds of outages without needing to do checkpoint restart or other expensive mechanisms. And the application will essentially delay while it's trying to recover the connection, while it's trying to wait for the connection to become viable again, and then will resume without any effect on application data or reliability. There's other techniques such as diversive routing and some other things that are built in here. There's an independent progress option so that the application can make progress on communications without calling into the communications library. We have carried forward a lot of algorithms that were developed over many years to have good tag matching algorithms that work well with a wide range of applications and have been tuned for some of the more challenging timings between when the sends and receives occur relative to each other. Internally, there's a credit-based flow control mechanism at the PSM level for those UDQ pairs. This helps to avoid incast so that the recipient doesn't get bombarded by too much traffic and allows the recipient to do some pacing. The receiver side Rendezvous implicitly has a pacing mechanism to it in that we can control how many CTSs are outstanding at a time, how big those RDMAs will be, and this also helps to avoid incast. I talked a little about the pipelining, and so we can stripe large messages across multiple rails. We can have multiple clear to sends for different parts of the message, which also then helps to pipeline some of the overheads of setting up the message and the RDMA. There's multiple modes. The mode 0 or the first mode is using a UDQ pair only. This is the most scalable, has the lowest memory footprint, and for many HPC apps that tend to do medium and smaller messages, this actually performs extremely well. For the next mode turns on the Rendezvous module, which is optional. The Rendezvous module is then used for RDMA for larger messages. The default thresh transition points at 64,000 bytes. But we have seen some applications where tuning it down, such as 8,000 bytes, can be effective. This has very good scalability in terms of memory footprint, and for applications that are bandwidth intensive or may have a single rank doing all of its transmissions at a time, this provides the best bandwidth. And so this is also tends to add some improvements for various applications. We have two modes that are kind of experimental. They're demonstrable, they work fairly well. There's more tuning to be done. We basically found that the first two modes provided all of the key benefits. So we kind of left these in more of an experimental state. The first of which is can use user space RCQ pairs in addition to the UDQ pairs, though in this case they'll only be used for Rendezvous. We can still use the MR caching in the Rendezvous module or can turn that off. This has a notably higher memory footprint as you scale up processes per node and the job size. In some cases, if you've only got one rank communicating, this may have a hair less latency, but we found as we increase the number of ranks communicating, the inherent queuing and other behaviors that have to occur in order to get mobile processes out a single NIC kind of wash out some of that. And James is going to be talking tomorrow morning a little bit about some of the performance comparisons that we've done between this and some other libfabric providers. And the last mode is to have a user space RCQ pair used for both eager and rendezvous. We'll still have the UDQ pair for some of the control things, such as the credit exchange. This provides a little bit lower latency for those eager messages, at least on some of the NICs that we've tested. It's also the least scalable and the highest memory footprint. And we've found that while this may do a little better on some micro benchmarks, that really mode 0 or mode 1 do equally well on real world apps, which is where we're trying to focus our tuning. Inside there's multiple connections and load balancing mechanisms so that we can have multiple queue pairs per remote endpoint that we're connecting to. This allows some of the striping I was mentioning before. When you've got multiple processes sending large messages, it helps to remove some of the head of line blocking, helps to get more things flowing concurrently. And we can also even do the same behavior for the user space queue pairs and have multiple queue pairs. This we experimented with, but tended to find that for real world use cases, it provided limited benefit because you already have multiple processes, each with their own set of user space queue pairs. And so you get the inherent benefits of striping things out of that aspect. The MR cache is used for modes 1 through 3, although it can be turned off in modes 2 and 3. And this is hooked into the kernel using the MMU notifier hook so that we can accurately maintain the cache and remove entries consistently when the application frees memory. Next slide. This is a view of the insides of the user space provider for PSM3. There's a number of key subsystems. There's a endpoint and connection management that mainly occurs at the beginning of the job, but if you've enabled lazy connection establishment, it can be invoked as connections are used for various traffic patterns, so that we can delay connection establishment for apps that don't need, for example, all-to-all connectivity. The heart of most apps will be using the MQ, the message queue mechanism, which is a two-sided messaging capability. There's also an active messaging capability, which is used to implement one-sided and can be used for some other capabilities. And then there's an information query component that provides support for some of the OFI query functions that may be issued to understand the state or status capabilities of the provider. The heart of the discussion is usually around what we refer to the NIC messaging path. This component deals with all of the strategies for moving data between nodes. There's also a SHMEM, shared memory implementation that is focused on intranode communications. In some environments, that may be handled by the middleware. In other environments, the provider may be requested to do that. And then for compliance with things like the MPI spec, there's a self one that allows you to send a message to yourself without any issues. Again, that may sometimes be handled in the MPI middleware above, but it's here for completeness. There's different protocols. There's a tiny protocol that is oriented towards optimizing 8-byte messages and less. There's an eager protocol that I spoke about, and then there's the rendezvous protocol. And below rendezvous, there's actually two strategies. We're usually focused very much on the RDMA strategy that I showed in the ladder diagram before, but there's also a long data mechanism where we won't try to use an RCQ pair, but we'll take advantage of rendezvous as a way to pace the receiving of the data and to make sure that we don't need an excessive number of receive buffers before the tag is matched on the receive side, so we can pace some of that. Below it, we are taking advantage of the queue pair handling. There's a set of functions that deal with the basics of interoperating with the verbs queue pairs. And then there's some MR memory registration management. There's actually a reference counting mechanism in user space. So if the buffer is used more than once concurrently by the app, we won't have to call into the rendezvous module or into the verbs interface. and then we can do the caching through the Rendezvous API. And there's some supporting functions around logging. There's a rich set of statistics that can be gathered and reported runtime, so that can aid you to tune your applications, understand if you're encountering, if you have a lot of eager traffic, if you got a lot of rendezvous, are you encountering packet loss and recovery, or other interesting events that can give you information to tune your application. Next. This is a simplified UML diagram of the key data items in the Rendezvous module itself. Things start at the top with a user opening an instance of the Rendezvous module. User jobs then associate themselves with a quote job device. This represents a given shared resource. It is a single NIC being used by a given job. There may be multiple user processes associated that are part of the same job, and jobs are identified by an authentication key or a UUID that comes in from the libfabric provider or from the job scheduler or the middleware, along with the user ID of the user code that's running the given process. And this is associated then with a single RDMA device, and there may be a listener that is supporting connection establishment for it. A given user then requests to make use of connections, and associations are established between connection and single connection resources. A single connection is a single RCQ pair and its corresponding resources. And then a connection may have a collection of up to 16 of those that are being used for striping data for a given communication path. So the user process only really sees the connection object, and inside of the Rendezvous module, the striping occurs. And then on the right size picture, we have the memory registration cache, which tracks a per user process. There's a separate instance of the cache because it's holding memory specific to a single process's address space. And then we cache the verbs MRs with their identifying information. And we, of course, reference count them against the outstanding writes so that we will not release a MR from the cache while there are IOs in flight for it. Okay, next slide. This code is all available upstream now. It's been included in the libfabric 1.12.0 release. There's a couple of refinements occurring that are targeting a 1.12.1 to introduce some support for a couple of extra distros that some participants in that community have asked for the ability to build on. There's also an out-of-tree version available of this at GitHub. That one has been designed so it can run on existing distros and the existing version of libfabric already included in those distros, such as going back to as far as Red Hat 7.9 and the more recent Red Hat /15 and some others. We did just work with the maintainer for libfabric to design an out-of-tree build mechanism that's actually also present in some of the code that we put into the libfabric repo. So that repo is very consistent with the libfabric one. We're in the process or beginning the process of engagement on the Rendezvous kernel driver. That's available out of tree now and will run against the in-distro versions of OpenFabrics, including those in Red Hat 7.9 and newer, /15 and some others. Surrounding this, I may have alluded to it earlier. We do have a set of tools in user space that we refer to as Fast Fabric that can help people administer, deploy, and verify performance and diagnose performance and other basic issues. That's also available upstream in the GitHub. And for reference and assistance, we've gathered together a few third-party benchmarks into an MPI apps repo that can help people to do basic testing and verification of their cluster. Next slide. So in summary, this is a new provider that fits into the libfabric and OpenFabric's infrastructure very naturally. The kernel module is optional, but can help optimize large transfers by taking advantage of RDMA in a scalable manner. There's a lot of features. I really didn't have enough time to cover all the capabilities, but it's very feature rich by building off of a mature foundation. We focused our efforts here around Iraqi, and that's where we've done our optimization and performance scalability with a focus around some of the recent Intel NICs, but it will actually run on standard verbs interfaces. And it is available upstream now, so if you want to try it out, it is production worthy and available upstream. I want to really thank you for your time today, and I wish you all to stay safe in these challenging pandemic times.
Thank you, Todd. Any questions for Todd? Going once, twice. All right, and thank you, Todd, for your time today.
Okay, thank you.